In this video, we are going to talk about analog and mixed signals and how to design this kind of boards and how to do layout, how to do placement. And I'm going to talk about this topic to Artur because he's really good in designing all these analog boards, and he's going to help us to understand this topic. Is it right, Artur?
Yeah, thank you. Okay, so let's start with the floor plan. When you're doing a PC board design, the first thing you should really do is segment out your analog and your digital, your power, and really you want to prioritize the most sensitive connections first. I think sometimes in retrospect, it seems like an obvious decision, but very often they're just trying to route whichever signal they see, and they don't think about the sensitive signals first. So by sensitive signals, we want to keep the higher speed digital signals away from our most sensitive analog. And so we think about what type of analog do we have? And this particular example has a 24-bit converter, analog to digital converter, and a 14-bit analog to digital or digital to analog converter. And so the 14-bit is obviously lower resolution and less sensitive, so that can be a little bit closer to the digital. And the 24-bit, we want to try and minimize the digital higher speed signals from being close to that. And then if you look at the analog, you'll notice that the filter on the A to D converter is really close to the input. And so that means that any noise picked up between the analog to digital converter filter and the A to D converter input is going to be minimized. And then the amplifier is going to be close to the analog connector, because the amplifier might be in high gain. So maybe the amplifier is in a gain of 1,000, and so millivolts are on the input and volts are on the output. So the millivolt signals are the sensitive ones. That's what we're really talking about. The worst thing you could do, for example, would be route a high-speed digital signal next to a millivolt level signal. If you route a digital signal near a 10-volt or a 5-volt analog signal, it's nowhere near as bad as if you're routing it near millivolts or microvolts. It's going to be much more sensitive to the noise pickup.
So basically what you are saying, when we place the amplifier very, very close to the connector, the track on the PCB with 1 millivolt signal will be very short, so there is like very small chance to pick up noise, a lot of noise from the board or from other signals.
Yeah, absolutely. Absolutely.
Okay, and I would like to point out, so basically in this layout we can see that, for example, we place the analog into the corner. So we didn't place the analog circuit somewhere into middle of the board. We place it somewhere completely like kind of separated area. It's not really separated, but it's like corner, so no digital signals are routed through this area. I think that's what is important, correct?
Yes, absolutely. And to your point, there should be one solid ground plane for the entire board. That's our general recommendation. There's a few, let's say cases where maybe you're dealing with really high power signals where we might route a split in a board, but for all the analog to digital converter mixed signal systems, we recommend a solid ground plane. A lot of systems have switched power.
Okay.
And when you have your A to D converter and your amplifiers and so forth, in some lower cost systems or lower performance systems, it might be okay to connect that switch power directly to the amplifiers. But frequently what you want to do is have a linear power section. And that's going to get rid of the majority of that switched noise. And then the power supply rejection of the amplifiers and A to D converter and voltage reference and so forth will help clear things up quite a bit. So at really low frequencies, the signals on your ground return path are going to follow, kind of flow across the board. And what we mean by low frequency is 100 kilohertz and less. And Mr. Henry Ott, he did a great job of explaining this in his book. For higher frequency signals, the signal is going to travel really tightly underneath the trace. Now, I marked this as ground plane, but this could also be a power plane. And that's sometimes where the biggest problems happen, is because the power plane might be segmented into multiple different power regions. Let's say a 5-volt analog plus or minus 15-volt analog. Whatever the closest adjacent plane is to the trace, is where the return current flows. So a lot of people naturally assumed, I used to assume, that this return current would always flow through the ground plane. And that's true if the ground plane is directly beneath the top layer. But if the ground plane is down several layers and right beneath the trace is a power plane, that's where the return current will flow. So that can be a concern if we have splits in the plane, because splits in the plane are, I think, probably the #1 problem for EMC issues. I'll just show this briefly. This is the side view of the board. And you can see how the field looks. And one of the things that I didn't realize years ago is that the dielectric thickness, in other words, the distance between the top trace and your ground plane, it actually makes a big difference in how your fields spread out. So the thinner this is, the tighter your fields will be. And, it's still, they're going to be either way, if it's a little bit tall or if it's very close. It's still going to be confined near the trace, but it's much better if it's a thin dielectric thickness.
So when we bring the tracks closer to the ground plane, we are going to have better, or the noise around the track is not going to spread so far away.
Exactly. And this slide shows measured results where I applied a square wave, 50 megahertz square wave, onto one gate driving a long trace. And then there's a adjacent trace with some thin spacing between the two. That's the victim. So this is the aggressor and this is the victim. It's just grounded. There's no signal on the victim. And so I looked for crosstalk. And so crosstalk's listed in volts peak to peak on the vertical axis. And then I checked it versus a variety of different things like trace length and trace spacing and so forth. So, this one's kind of straightforward. The longer this trace is, the more coupling you're going to get between these two traces. And so because there's more capacitance and more mutual inductance between the two traces. So if we look at about 1,000 mils, we're getting only 0.15 volts peak to peak. But if we go to 3,500 mils, we're getting on the order of 0.45, and that's on a 3.3 volt peak.
So basically what we are talking about is this is the noise picked up from the aggressor line. It's the noise picked up on the victim line, and basically it's going to be 0.15 volt for if the tracks are routed close to each other only for 1,000 mils, correct? Okay, perfect.
That's correct. And you'll notice there's two graphs here, and the two graphs are for the two different dielectric thicknesses. And so the thin dielectric is much more susceptible than the thick dielectric. It makes quite a difference. Then I did the same kind of thing, but I kept the maximum length between the two, but I adjusted the spacing between the traces. And so this is a 8 mil spacing. And again, you can see the thick dielectric is much worse than the thin dielectric. And in fact, for the thin dielectric, as soon as we start to move those traces even a little bit apart from each other, you almost get negligible or unnoticeable crosstalk. And so one of the reasons I'm showing this crosstalk here is, of course, if you have two digital lines in parallel, you'll have that kind of crosstalk. But if you have, where it really is a problem is if you have an analog line in parallel with the digital line, then, you know, when we're dealing with microvolts or millivolts of analog signal, you know, even 0.1 volts of crosstalk is horrible. So you really have to make sure that you don't have that happen. And just as we saw, you know, if the majority of the return current is confined beneath the aggressor, and we keep the analog traces fairly good distance from the aggressor, we're not going to have any crosstalk or coupling into the analog.
Okay, I understand now.
So there's the floor plan. Let's see, and here I think we should continue on with this because this talks about the solid plane versus the with the split plane.
Yeah, I would like to point out. I think now many people, they know solid ground plane is better, but I still would like to talk about this because there are still many data sheets and white papers and documentation telling split the planes or use analog and digital planes. So let's talk about this.
Yeah, it's true. And even, you know, even some of our older literature does show it that way. And it was an idea in the past that, you know, was a good approach, but it's not. And in fact, often I've solved, so customers, you know, of ours do this. You know, we do see this happen. And the absolute worst case scenario that I've seen, and I've seen it a number of times, is where they connect the analog and digital plane together with a ferrite bead. And so any signal that's traveling, you know, across that gap, the return current has to go through that ferrite bead. It develops a large potential difference. It causes even data integrity issues, or in some cases it actually damages the part. You know, there's enough of a potential difference to exceed the absolute maximum specs.
We had ESD failing issues exactly when we used ferrite bead under audio chip. It was a long time ago when I was starting with hardware design. So I can confirm, yeah, it's a problem.
In those cases, just replacing the ferrite with a 0 ohm resistor often resolved the problem, or at least improved it. Great. Okay, it's interesting. Yeah. You know, and sometimes customers refuse to get rid of the split.
Analog and digital. Okay.
Yes. And so what I suggest, if you really feel you need the split, and I would argue that you don't, but if you really feel you need it, is to have a bridge, a significant bridge that allows any signals digital signals that have to bridge the gap to go across that bridge. But then the best result is to just use a solid plane. And that's what we do even on our very high resolution, extreme low noise boards, is just use a solid plane.
Okay, so again, I would like to point out, if someone needs to design mixed board, analog and digital, then solid ground plane is still good solution, even if people may be worried like, oh, my currents are going to be mixed together and all the noise is going to travel to my analog part. And again,
yes.
When we were talking about this ferrite bead, I have one more story. So one problem was the ESD, and we had also second problem, and it was EMC. EMC issues, because the analog ground plane actually had like different potential, and cables going out from the analog ground and cables going out from the digital ground, they actually somehow created some fields, and we failed EMC.
That makes sense. This is basically like a bipole antenna. So yeah, and in fact, so this shows what would happen if you ran over the gap. The return currents have to go around, and even maybe more important, this gap creates an antenna that broadcasts the noise. And if you were to design antenna, the Vivaldi PC board antenna is very similar structure to this.
Mm-hmm. So
And
go back,
I
go
did a
back, go back,
measurement.
go back. So
Sure.
again, I would like to maybe describe a little bit more what we see here. So this could be, for example, a situation when we have power planes under
Yes.
the tracks. So if we don't use solid ground plane, but we have power planes, and usually there are a number of different power planes. So there would be these gaps in the power planes or between the power planes. And if we route if just above these power planes, we route some tracks and we route these tracks about these splits, then the return currents, they have to find different way how to flow. And as we can see on this picture, they all mix together and they also go out through this gap, and
Right.
they make a lot of problems. And there are reflections, and I think all the kind of I've done some videos with Eric Bogatin. He has exactly these
Yes.
simulations, and so if people would like to understand a little bit more what is happening about this gap, they can watch these videos.
Yeah, they're great videos. I've watched them myself.
Me too, me
I
too,
did an
several times.
experiment. I did an experiment here where I ran across the solid plane
Mm-hmm.
and across the split. And this was measured with a little RF sniffer probe.
Mm-hmm.
And this is the baseline at about minus 55 dBm. And we basically almost pegged the instrument here when we're going across the split. And the noise pickup is about 56 times greater than when we go across the continuous, which is only minus 39 dBm. So even going across the continuous plane, you're going to still emit some, but it's quite substantially larger. And I've seen, as you mentioned, like if people are going over a power plane, you might have multiple splits that you're going across, and that becomes really difficult to get good performance when you do that.
Mm-hmm. Mm-hmm. So basically, you actually built these boards and you measured real physical boards. These are the measurements, no simulation.
Yeah, yeah. Same thing with the previous one with the crosstalk. I did that. So
Uh,
actually, this finishes this section. Although I had some layout related stuff before that. Should we go over that?
okay.
Oh wait, not
So
this. Hold on.
So we
This right
finished the
here.
one of the most important parts, like
Right.
understanding uh, placement of the components and understanding importance of the ground plane and understanding how signals travel through our board. So to design a mixed board, there are some other considerations what we should be thinking about. And the next one is what? PCB
Well,
layout.
it's layout, PCB layout issues related to amplifiers.
Okay. Because you are expert for amplifiers.
Yes, it's something I spent a lot of time on, as well as A to D converters. Those are the two areas I've focused my studies on.
Okay.
So this shows an op-amp layout. And just as I kind of mentioned earlier, there's certain things you want to prioritize. And with op-amp layout, the first thing you want to do is place the decoupling. And then the second thing you want to do is just prioritize the length of this inverting node, because this inverting node can cause instability if it's too long. Parasitic capacitance on this inverting node can cause the amplifier to oscillate. And it's especially true with high-speed amplifiers, but even moderate speed amplifiers can have this problem. So here on the top is a little bit problematic layout. If you look at it, it actually looks pretty tight. It doesn't, it doesn't on the surface look like a really bad layout. And then this layout right here doesn't look much better. You might even say that it's worse. But here's the key point. This part that's highlighted in yellow is the inverting node, and it's circled in white here. And that's going to have a longer capacitance to it. And of course, this isn't really even that bad, but this could cause a high-speed amplifier to oscillate. Now here, it's really, really tight, that section. And in many cases, especially for high-speed amplifiers, it's one spot where I would suggests that you might need to mill out a section of your ground plane or power plane beneath these traces. It's the one kind of exception to that rule, because if there's a lot of capacitance on this node, you can get an oscillation. And so it's a common practice for the high-speed amplifiers to have this little slot, which could potentially pick up some noise, but the oscillation aspect of the amplifiers is worse.
That's interesting. So for these very important nodes, you can actually remove the ground under them. Okay.
Yes. Now, here is proper decoupling. I think most people know this, but I do see it routed improperly in some cases. And so obviously you want really long, thin connections to your decoupling, and you want to make them thick and you want to make them short, but you also don't want to connect your decoupling directly to, or your power rail directly to, power plane, power rail directly to the pin. You want to connect it as shown over here to the decoupling. And of course, multiple connections always is going to give you a much lower inductance than even one large via. So, I don't always do this. It kind of depends on the situation as to whether or not I'll put multiple ground plane connections and multiple power plane connections. But if it's a critical decoupling, it's not a bad idea. And then here's the one that people tend not to let go of. And I know Eric Bogatin did a really great Altium Live, and he's done this on your channel a bunch of times. And the idea is putting these many parallel decoupling capacitors, a large capacitor, a small capacitor, a smaller capacitor. And it's kind of a throwback to olden times. And it can, by putting these two parallel capacitors, create a resonance, which is a problem. And it can actually increase the noise. But what I think the most compelling reason, and the way that I convince most of my colleagues, because a lot of people still want to hang on to this, is it just wastes board area. So here's a PC board where we put the two capacitors in parallel. And you might have, this only shows two power rails, but you know, the A to D converter could have multiple power rails, let's say 4 power rails. And if each power rail has 2 capacitors, I've seen even sometimes 3 capacitors, it becomes really difficult to do a good layout. Now, if you look at this layout, it doesn't look horrible. It's pretty tight, really. Everything's squished in pretty good. But these capacitors make it difficult to really route well. And I would say that the input filter is prioritized as being close as compared to the power supply decoupling. And I would always prioritize the power supply decoupling first, and then second, I would prioritize the input filters and try to make them symmetrical and close as possible. Here's a better layout.
Did you try some measurements? I'm just curious if you really,
you know,
compare these.
I have done boards before like this where I've tried a variety of different, you know, different experiments, but the ones that I showed earlier, where they're very simple experiments, yield more interesting results than what I got with this. So usually, sometimes you could do a really bad layout and
everything still works,
actually
okay.
the part's pretty great. Yeah,
I'm asking because actually I've done some simulations on these via connections around the coupling capacitors, and actually there were no like big differences, because the most important thing was if everything was connected on the top layer, on one layer, it was the lowest inductance. So it really didn't play a role where exactly the via was. But if it was powered from the other layers, then there it was problem. So if everything was routed on same layer, no problem if capacitor was like very close or via was a little bit different. But yeah, but there are, I think this was only one point of view, because I think there are more things what play role like as you say, like if you have more capacitors, then there may be, for example, the mm, how is it called? I forgot. Resonance. Yeah.
Yes. Now, truthfully, I've not seen, and I want to study this area a little bit more, but I've not seen most of our most designs have multiple different types of capacitors on the power rail,
Mm-hmm.
and I haven't really seen much issue with that.
Mm-hmm.
At least not that I was able to measure, but I definitely know that it's, having fewer capacitors. I don't think impacts
Mm-hmm.
negatively anything. I think it makes it better, if anything. But especially, it makes it easier to lay out,
Mm-hmm.
and tighter to lay out. And I mean, I have seen problems, but whenever so far at least, and I have limited time to just do, like random experiments, but so far I've not been able to really show a really bad versus good,
Mm-hmm.
with this type of
I
thing.
understand. I understand.
Okay, and here shows the same layout where I
Mm-hmm.
eliminated those capacitors. That was the only change made. And you can see the decoupling's nice and close. I'm using multiple connections to the ground plane. And I would say for a higher speed device, these kind of things are much more important than they
Yes,
are
I
for
agree.
lower speed device. And then the filter is a little bit deprioritized, but that's a very short connection, so it's not a big deal. It's just that we prioritize the power supply connection.
Mm-hmm. Okay.
And let's see, I think we talked about that already. So that's it.
Decoupling.
Yeah, that's it from the layout perspective. And so maybe another interesting thing that I'd like to mention is electrical overstress.
Okay.
Um, and I put that as the number one item. Um, Truthfully, not because I necessarily think it's the most important. I think it's probably the most overlooked.
Ah, okay.
People don't usually think about electrical overstress until they're either having failures out in the field, or maybe they're failing their EMC tests like surge or EFT or ESD testing,
So what
in
does
the
it mean? Like
compliance
why
area.
this is important for mixed board design?
Well, as we saw on that layout example earlier, the floor plan, there's going to be a connection to the outside world, from the digital world and from, probably more importantly, the analog world. And the analog world, devices can get uh, long cables connected to the amplifier, the op amp, and the long cables can pick up noise. Surge is meant to simulate a lightning strike, and other very high intensity issues. And then EFT is like a motor, and then of course ESD could be any human touching the cable or input connections. And any input connection, and really even any internal connection, but less important for the internal connection, is susceptible to damage. And of course, another form of electrical overstress would be to just miswire your system. So somebody might build an analog input module that's meant to take 10-volt input, and maybe they connect their 40-volt power
Mm-hmm.
supply to that 10-volt input. So that would be a continuous fault. And surge or EFT would be a transient fault that only lasts for a very short amount of time, but is high intensity.
Mm-hmm.
So
And this is even
so
more
it's
important
best to,
for analog components because they are like much more sensitive. I guess if input is only a couple of hundreds of millivolts or something, you really would like to protect this kind of input. That's why it is very important.
yes. And I would say that it's probably many systems experience an electrical overstress that it still functions after the overstress. But what can happen is the input can become leakage, it can have a leakage current, or the input device could be subtly damaged. and on a digital system, you probably wouldn't notice any effect like that. But on an analog system, that leakage current could really impact the accuracy, or
Mm-hmm.
a subtle shift in the input performance could impact the accuracy.
Mm-hmm.
So of course, they're both important. You don't want to damage anything, but I just feel like analog is probably more sensitive, and that might be partly because that's the world I live in. So, it's my bias. And so here's a typical kind of protection.
Okay.
There's multiple different kinds of devices. A very common type of device is a TVS diode. A transient voltage suppressor is what that stands for. It looks like a Zener diode, but it's meant for overstress events. So it acts quickly and can dissipate large amounts of power. In fact, they're normally rated for things like surge or EFT. So they're rated for a short duration, large current event. So they're rated for a tiny little device is rated for hundreds of watts, but hundreds of watts for milliseconds.
Mm-hmm.
And so usually you want to put some kind of current limiting device before the
Mm-hmm.
TVS to prevent the TVS from being damaged. And then as a second layer of protection, the amplifier or A to D converter itself has a built-in ESD protection circuit.
Mm-hmm.
And it's not going to necessarily withstand something like a very large overstress. So you can't just rely upon this to work by itself. But you do want to limit the current flowing into those ESD protection circuits
Mm-hmm.
as well. And then,
I have a question before
normally,
we move to different
sure.
one. So how do we come up with numbers for these resistors, and how do we choose the proper,
Yeah,
components?
it's a great question. So the TVS diode itself has, I wonder if I have a curve. Do I have a curve? I don't think I have a curve. It has a standoff voltage, which is the normal operating voltage when it's not under a fault condition. And the standoff voltage might be 5 volts, for example. And that means that you could connect it to a 5-volt power supply or a 5-volt input. And at 5 volts, there's a defined leakage current, so that your performance is not going to be impacted by that, or you'll know what the maximum leakage is, and you can understand how it impacts your performance. So that's the standoff voltage for non-fault conditions. And then there's a breakdown voltage, which is when it's going to start shorting out and limiting the voltage in. It's basically equal to kind of similar to the Zener voltage on a Zener diode. And so the standoff voltage might be 5 volts, and the breakdown voltage might be 7 volts. And so if we applied a 50-volt input signal, it would break down to 7 volts, or depending on what the current flow is, it would go a little higher than that. And that's probably good enough to protect the input of the device.
But I think there are
Now
also other parameters like capacitance or something what is important for.
Sure. Yeah, the capacitance is important for the distortion performance. So if you're, for example, placing a diode on the input of the op amp, and it has a large capacitance, unfortunately, that capacitance is not going to be constant with changing voltages. So as the voltage at the input goes up and down, the capacitance of this diode would also go up and down, which introduces distortion. So if you have a system where we're interested in like AC performance, let's say an audio system, for example, that could be problematic. If it's a DC input signal, let's say it's monitoring temperature or some sensor that's a very slow moving sensor, the capacitance isn't as much of an issue. So it really depends on the situation as to that. Now the resistors will be sized to limit the current, so you'll need to know what your fault voltage is, and then you would look at what power dissipation. You also need to know, is the fault a continuous fault or is it a transient fault? It's much easier to protect against a transient fault than a continuous fault. If I put 50 volts continuous, I might need to have a fairly good sized resistor that'll dissipate some power, physically large resistor that'll dissipate the power to protect
Mm-hmm.
this TVS diode. If it's a transient fault, then it's only there for a few milliseconds and you don't need to worry as much about the power rating of the resistor.
Mm-hmm.
I mean, you have to worry a little bit, but not as much. Now, one thing I should have shown here, which I do show over on the A to D converter, is you should really have a TVS diode on every supply rail as well. And the idea is that if there's a fault that is applied to the input of the device, it's going to route through this ESD structure to the
Mm-hmm.
power supply, and you need to protect the power supply from that. And now the LDO or whatever power device is connected to the power rail may not be able to respond fast enough to protect the power rail from that transient. So you need a TVS on each power rail as well. There's other protection circuits, such as, what is it called? A PTC fuse, which is a resistor that'll increase its resistance when high current flows through it. So that's a good device. I think I listed a few of them here. Let's see. Gas discharge tubes, that's one I actually haven't used. Just a resistor or capacitor or inductor actually is it often works quite well as a protection circuit.
Mm-hmm.
And I would say that the input ESD structure in some cases can be effective, but usually it has to be for even an electrical overstress event. But usually you want to put a current limit device, and these are normally rated for 10 milliamps input current continuous. And so people will, if they want to use a very simple input protection, they put just a resistor and maybe a capacitor on the input and rely upon the ESD structure to do the protection.
Mm-hmm.
It really depends on what kind of environment. You know, do you really need these TVS on the input? Is a simple resistor good enough? And everything you add, as you mentioned, is going to impact the performance. So you have to think about the performance impact. And that's probably the reason why they're usually an afterthought, because, you know, people don't want to use them because, you know, it might impact the performance, but then their device is getting damaged and,
Mm-hmm.
and that's not good.
Mm-hmm. Mm, okay.
So, so some other things I'd like to mention just briefly is the component specifications. So I remember the first time I looked at an amplifier data sheet, there were so many different specs, it just overwhelmed me. And it's like, well, how do you kind of navigate your way through the data sheet? And the best thing to do, I think, is to understand the different categories. So the ABS max rating is what we just talked about. That's the rating that if you exceed it, if you exceed the voltage on the input, it'll damage the device. And then most of the specs that people care about are the linear input. Well, actually, the linear input and output range is another very important spec, because on an amplifier or a linear system like an A to D converter amplifier, D to A, the output can only swing so close to the power supply, or the input can only swing so close to the power supply. And so if you violate these two things, input and output swing, or stability even, the circuit won't function. So there's a certain set of specs that relate to the functionality of your circuit that, you know, besides looking at the ABS max, the next thing you should do is look at confirming that your circuit will be functional across temperature and across process variation. And then power supply voltages and currents will define, you know, ranges of devices. Like there's, for example, amplifiers come in kind of 5-volt categories where the maximum supply operating voltage would be 5 volts. And then they come in 15 volt, plus or minus 15 volts, or 30 volt type amplifiers. And then they come in 100 volt categories. And so you could kind of sort through what devices make sense for your application. Temperature range is important. And then the rest of the specs have to do with performance. And so one way of kind of whittling down those specs and reducing them to a smaller list is to decide, is my circuit AC optimized or DC optimized? And that will basically cut the number of specs in half. And so an audio system, for example, you really only care about the AC specs. The DC specs are much less important. But a sensor system, for example, where you're measuring temperature or a pressure or something like that, the DC is really most important and the AC is less important. And so there are some systems where both are important, but that's kind of what I do. I try to break it down into different categories and then and look at each one. And I guess last thing I'll mention about that is we have a whole series of videos called TI Precision Labs that actually goes through all these different specs. And if currently you look at an op-amp data sheet or an A to D converter data sheet and are a little bit overwhelmed by it, if you watch the video series, I think it would make a lot more sense afterwards.
Yeah, okay. So these are all important when selecting components for analog part of your board. And I think there are also
Yes.
some other things. You mentioned you have some kind of demo to show how the power supply what rejection works or something. What do you
Yeah.
can think about?
Yeah. Let's look at that. So, so
What does it mean, power supply noise rejection?
let me go to this section here. So I'm going to show a few slides before we do the demo. So in case some members of the audience aren't familiar, there's a way of representing large numbers called decibels. And basically, usually it's for gain, but it could be for other attenuation or other things. And it's just 20 times the log of the gain, log base 10 of the gain. So a million is 120 decibels.
Mm-hmm.
100 is 40 decibels.
Mm-hmm.
A gain of 1 would be 0 decibels. So if we look at common mode rejection, well, first, what is a common mode signal? For an amplifier, this is a instrumentation amplifier. The input signal that we're trying to amplify is a differential signal. It's the difference between the plus input and the minus input.
Mm-hmm.
And so this could be millivolts or even, it could be volts or perhaps hundreds of microvolts. And the amplifier could be in a very high gain. And so that's the differential signal. The common mode signal is a signal that's connected to both of these two signals,
Mm-hmm.
to inputs. And now, if you do your PC board layout right, these two traces should be symmetrical and they should be close together. And so if they're symmetrical and close together, when noise is applied or to these two to these lines, the noise pickup should be relatively equal in amplitude on both inputs.
Mm-hmm.
And so ideally, if you look at an ideal amplifier, if the signal is the same on the minus input as it is in the plus input, then what'll happen is you'll subtract the two and it'll just completely cancel.
Mm-hmm.
But real amplifiers don't work that way. They can only reject so much of this common mode signal, the signal that's common to both inputs. And so a real amplifier, if we look here, it's close to 120 decibels of gain, which would be an attenuation of 1 million. So if I had a 1 volt signal on the input, the output signal would be a microvolt or a 1 million attenuation. So at low frequencies, the common mode rejection of this device is really quite good. And beyond my demo's ability to measure, it'd be inside the noise of the amplifier. But at higher frequencies, it starts to attenuate, and that's unfortunate, but it's just a natural part of the way any amplifier is designed. And there's not much that we can do about it. We hope, if you're doing a comparison and if noise is a concern, you could look at this common mode curve and see what frequency is, let's say, the switching power supply at, or what frequency are potential interference sources. And you look at your common mode rejection at that frequency, and you see how much attenuation can I get at that frequency. And so if you look at this curve, I have the simulation results, because we could simulate this model. I've got the measured results that I did with the demo I'll show you in a moment. And then I've got the datasheet curve. And all three of them don't match perfectly, but you can see they're reasonably close together. So before I show the demo, I'd like to show the power supply rejection, which is very similar.
Before we move, can you go back?
Sure, yeah.
So I just would like to clarify. So if I understand right, it means for lower frequencies, the noise which is coming inside of your amplifier will not be transferred to the output. But for higher frequencies, noise coming into input may transfer to the output.
Okay. Yes. So, for example, a gain of 20 would be an attenuation of 10. A gain of 40 would be an attenuation of 100. So, at about a megahertz, we could expect a signal to come out about 100 times smaller than
noise.
Common
if we are talking about noise, then it means noise.
Right. Okay. Now I want to clarify though. The amplifier itself and the resistors around it will generate noise. We call that intrinsic noise. And so there's nothing we can do about that. It's random and it's uncorrelated on the two inputs. What I'm talking about here for the common mode signal is noise pickup from an electromagnetic interference that's equal on the two inputs. So it's equal on the two inputs, and that means we can cancel it with common mode rejection.
Okay, I understand now. Okay, we can go to the next slide.
So power supply rejection is the same idea. And again, you can see it's in about 1 million at low frequencies. But really it's a noise riding on the DC power supply. The amplifier is all going to require a DC power supply. And unfortunately, our DC power supplies aren't perfect, and there's going to be some ripple on it. There might be a switched power supply noise, or a noise pickup, or noise from digital circuit switching, or whatever. But there's a noise on the power supply, and how does that noise get rejected? Well, we can look at the output signal as compared to the power supply signal. And so we got about a rejection of 1 million at lower frequencies. So if we have some low frequency noise riding on this power supply, it's going to come out 1 million times smaller. But then at higher frequencies, we're getting down to this 20 or 40 decibels of attenuation. So a gain of attenuation of 10 or attenuation of 100.
And these are like automatically built-in features, or you have to find special components which support these features?
No, it's automatically built in for really all amplifiers. They're all going to, and for that matter, voltage references and A to D converters, regulators. They're all going to have a power supply rejection. And for all amplifiers and A to D converters, they'll have a common mode rejection.
But you can compare different components. Some of them may have better rejection, and some of them will have worse.
Yes.
Okay.
Yes, and that can be an important criteria in selecting, the device. I had an issue some years back where I built a demo board, and the power supply was a little noisy, and the device was having some output signal that I didn't want, some noise on the output. And I went to a device that was not my first choice, but was a better choice because it had better power supply rejection. That was the key parameter. So there's so many parameters. You might, not be able to select the component based on the power supply rejection, but in some cases you will have to do that because maybe you have a very noisy power supply that might be a primary concern.
So let's continue in these slides what we have here, and then we will do the demo by the end of the call.
Okay,
Okay.
that sounds good.
So what is next?
So I wanted to talk about simulation.
So when designing analog circuits, you recommend to do some simulations. What do you use?
Yeah.
What is it difficult to set it up and run it?
No, it's actually fairly straightforward. Tina Spice is my favorite, although TI offers Tina Spice and also PSpice for free. And they have advantages and disadvantages over each other, but they're both great ways of simulating circuits. And the vast majority, if not all of our amplifiers, certainly all ones developed in recent years, have models available. And you can build your circuit, and you could apply for a transient simulation. You can apply for a let's see, AC simulation. You can do noise simulation. You can look at DC operating point. So you can really check out your circuit very thoroughly with Spice simulation. And so here I'm actually showing the circuit that we're going to demo. And this is a common mode signal. And we can see that if I do a transient simulation, I can, well, before I do the transient simulation, let me show you that the common mode input signal is a sine wave.
Mm-hmm.
And it's a sine wave with a 5-volt amplitude and a 1 megahertz frequency.
Mm-hmm.
And so we could have looked at that curve, and we could have saw what is the expected output. But in order to look at the transient output signal, I can just look at 5 microseconds from 5 to 10, and I can see what the simulation result is. So if I look at this, the input is common to both the plus input and the minus input at about 5 volts peak, and the output is about 847 microvolts. So
this is basically we have same signal on both inputs, but there is still this kind of small noise on the output.
Yes. Yes, exactly. And now,
and for a lower frequency, there should be almost nothing.
Right.
Oh.
Right. We could do that analysis. AC transfer. No. Let's change the frequency of this to 1 kilohertz. And we'll say transient simulation. And we'll say we're going to go from 0 to 2 milliseconds. And let's take a look at how that looks. And so now the output signal with a 5-volt peak in
75.
is 50. Yeah, it's 15. Well, this has got a DC. I should have probably.
Oh, because I saw there was capacitor or something in the circuit.
Yes. So there's a DC offset with the device, and so but the whole purpose of this output circuit, it's not really needed. I just wanted to make it convenient so that I could have an AC signal here. And
oh yeah, I understand, because it swings between 44 up to 75, so we wanted to move it to around 0.
Right. You can see this one symmetrical. So it's about 16 microvolts approximately peak, so significantly better than this one, which was 780
for lower frequencies.
So yeah, and then we could also look at the differential signal. Now this one is the actual signal we want to amplify. And so I can say transient and run this. And the input's a millivolt input. It's in a gain of 100. And so we're getting 0.1 volts out or 100 times a millivolt, 100 millivolts out.
Mm-hmm.
And so, so yeah, that's how you would do it. And then you could, you know, in your real circuit, you might have an actual filter to eliminate noise on the output or the input. You could do noise simulations. In fact, I could do a noise simulation right now, and you could see what the total noise of the circuit would be. When you see it kind of ramping up like this, but not flattening out, that means you need to go to a little bit wider frequency. So I'll just make it 100 megahertz, and we can look at the total integrated noise is about 800 microvolts RMS at the output of this circuit.
Mm-hmm.
So you could actually predict what the intrinsic output noise of the circuit would be.
What kind of components you can use in this simulator? I'm just curious. So switches.
Well, all your standard resistors and capacitors. These switches are convenient if you're, let's say, wanting to try different things out. So I could real time click on this switch and you know, open and close it, and you know, I could, for example,
so
I could
you
have
run
this
simulation
wired up.
when it is open, then you can run simulation when it is closed. Okay.
Exactly. And so there's AC, and you know, there's different types of control for the switches as well, and meters for monitoring different points. You know, different types of signal sources, current sources and voltage sources, and different types of semiconductor devices. You know, diodes and transistors and MOSFET transistors and, you know, bridge rectifiers. And these are
so you can also simulate AD converters and DA converters?
Yes, yes, we can. In fact, I wrote an AMP note on SAR A to D converter modeling. So I don't use these too often, but optical devices, and there are more different types of amplifiers. You know, for example, difference amplifiers and instrument. This is an instrumentation amplifier. All different types of amplifiers.
You can see my 555 with this one. Okay.
Yeah. Different types of output transistors and gates and flip-flops and so forth. You know,
click on ADDA. I'm curious. ADDA. What is that?
You know,
it was just before RF. ADDA. Click on ADDA.
Okay. Oh, all right. So I would actually suggest going to ti.com for the A to D and D to A, because all of the models that would work with TinaSpice and PSpice are on that, but not necessarily in this this section right
What
here.
does it mean? So you have to load the model specially inside of this symbol, or how does it work?
Yeah, actually a great question. So let me just try real quick, ti.com, and I'll say ADS 8860. That's just a A to D converter I'm familiar with. And it's fairly simple. I'll just go in here and I'm going to say, where are the models? So I'll go to design and development section of this landing page. And then I'll go to tools and simulation, and I'll say Tina reference design. So I'm going to go ahead and download this.
So you can download whole reference design.
Yeah. All right. So here is the A to D converter model. And if I say, let's do a transient analysis of this, what we're doing is we're actually simulating the switched capacitor on the input of this SAR A to D converter. And we're also simulating the switching events that happen on the voltage reference. And ideally, what you want to happen is you want good settling by the end of the switched event. Over here, typically when you download a model from TI, you're going to get something like this, where the simulation results that you would expect are shown over here. And so I'm going to shorten this a little bit so we can see a little better. And you could see the reference error. These are transients associated with the voltage reference. You could see the settling error on the A to D converter. And usually I like to make the settling error in
I have no idea what you are talking
microvolts.
about, actually.
Okay, sorry. Okay, so the main point is that there are transients on the input of the A to D converter that relate to internal switching capacitors. The capacitor's connected during the sampling portion, and then it's disconnected. And the connecting and disconnecting of that capacitor, it creates a current demand on the input of the A to D converter. And the amplifier has to supply that current, and this filter externally has to charge and settle to those transients.
Mm-hmm.
And if you're, let's say if you're taking a DC voltage or some sensor output, and we're trying to convert it to an analog signal with the A to D converter, or a digital signal with the A to D converter, we need to make sure that that whatever current transients on the input of the converter happen, that the voltage stabilizes on the input of the A to D converter and internally in sufficient time to allow settling so we get accurate results. And a similar effect happens on the voltage reference. And so so basically that's what these waveforms are showing. It's showing the settling on the voltage reference. It's showing the settling on the input, and that's really the challenge with an A to D converter is how do I know maybe what the noise performance of the converter is, what the settling is. The settling is usually the first thing that people look at, and even things like what's the offset, what's the gain error, and all that kind of stuff is simulated in these A to D converter models, which can be downloaded on TI. But back to the original question, A to D converters that are in here are maybe they're not the official TI models.
But it's good to be open the design, because I had no idea you can actually find some kind of reference designs for a simulator together with the TI components. That's really interesting. For AD converters, honestly, usually I just connect AD to, I don't know, sensor, like temperature sensor, and temperature sensor is not accurate anyway, so it doesn't really. But I'm sure in some applications like digital meter or something, people, they have to be sure what they are measuring is really the signal, and then maybe they need to go into these kind of details and investigate all the noises and everything.
Yeah.
Okay, we can go back to our slides, I think.
Okay.
So simulation, do you have something else to simulations, or it only
simulate? Nothing else for simulations. Okay. Well, just a general, it's kind of a top 10 list, general advice relating to lab measurements. Now, some engineers they'll go out, they'll build their circuit, they go to the lab, they get good results, and they say, okay, that's great. Let's put it into production. And you might even measure a small sample of devices. But the problem with relying upon lab measurements is you're not really looking at the real population of devices. Most devices, they're going to have, if you look at the performance, let's say offset voltage of a device, the most likely offset that you would get in this example, and this is typical of most devices, is 0. It's right in the center of the distribution. It's the center of the Gaussian distribution. In fact, 68% or plus or minus 1 standard deviation is going to be generally the typical that you see in a data sheet. So is equal to the typical spec. So you might measure 10 devices and they're all going to be within this typical, and maybe many of them will be close to 0 or in the center of that typical. Now, a much smaller percentage is going to be out near the limits, the maximum limit. So, it's very easy to get tricked into thinking that, your
Everything
performance
works.
is good, you haven't seen this, you haven't seen the tail of the curve.
Okay.
So that's why it's good to look at the data sheet, do simulation and measurement. Like the three-pronged approach is how I think of it. Calculation, simulation, and measurement. And consider the Gaussian distribution. You can even in SPICE do what's called a Monte Carlo analysis, where the resistor tolerance and let's say the offset of the device, different parameters, you can assign a Gaussian distribution to it. And the Monte Carlo analysis will do 1,000 simulations, and each simulation will give you a different result, and according to the distributions that you entered, and it'll give you an idea of how your system will act across process variation. And then kind of the corollary to don't just look in the lab at one device is look in the lab. So it's sort of the opposite of what I just said. You don't want to just look at the data sheet and do a hand analysis. You also want to check in the lab because there might be something you'll uncover in the lab that you don't see in simulation or you don't notice in the data sheet. Typical way that I like to look at my circuit in the lab is not just to look at things with a DC voltmeter. Don't just connect a DC voltmeter to the supplies. Look at everything with an oscilloscope. Look at the output with an oscilloscope. Look at the inputs with an oscilloscope. Look at the supply with an oscilloscope. Look at our signal source with an oscilloscope. And one of the reasons why is because amplifiers and other circuits can become unstable. So you might have a DC input signal and say, well, why should I bother looking at the input or the power supplies with an oscilloscope? Well, anything that's DC can also have AC on it. And so looking at the output of an amplifier that has a DC input with an oscilloscope might reveal a problem like a stability issue. And that happens normally when you connect a capacitor directly to the output or to the inverting input. And so, so I would say just, make sure that you look at all the nodes with a scope.
Do we
And then
need
kind of the last.
Do we need some kind of
Go ahead.
special oscilloscope or special probes? Can probes, I don't know, kind of damage the
Depends.
signal what we are measuring, or?
Yeah, it's a good point. It really does depend on the circumstance. For higher speed devices, it can be really challenging to get a good result with a standard 10x oscilloscope probe. And sometimes I'll use like a pin socket on the scope probe tip. Sometimes you might need a post amplifier on the probe because, the scope probes or a standard oscilloscope measurement can usually measure 10 or 1 millivolt per division. And so if you're looking at very low level signals, you really can't do it. Scope probe generally has a megohm input impedance. So if that loads your circuit, they also have a capacitance associated with them, which doesn't work for the higher speed signals. So it won't always work to just use a standard 10x scope probe, but it works most of the time, I would say. And here I think is the last one. Oh, no, I actually have more on lab debug. So one common, like people say, oh, I'm having
I know
DC
exactly what you are talking about. This happened to me. I learned the hard way.
The flux, the flux residue, that can be really bad. So use an ultrasonic cleaner, and even fingerprints, especially for very sensitive low current type circuits. The salt or the oil from your fingers can affect the performance. So this actually shows a measured result. One of my colleagues, Ian Williams, did this some years ago, but without any clean, this circuit had a DC input signal, and you could see the properly cleaned one is perfectly flat, but with no clean, we got crazy results that drifted over long periods of time. And that's usually the behavior you see with dirt or flux residue. is a long-term drift that changes with temperature and humidity and time. And then the hand clean was better, a lot better, but it still wasn't perfect. Using professional cleaning tool really made a big difference.
Mm-hmm.
And then the last one is there's an old saying, if it ain't broke, don't fix it. And that's actually a good saying, I suppose. You know, like you don't want to always reinvent the wheel when you're doing engineering. But I thought this was kind of interesting because I've seen multi-generational schematics that I've been involved in the design with, and customers I've worked with as well. And sometimes it's like, well, this circuit worked. We don't really understand what this circuit does or why it's there, but it works, and we don't feel like we want to take the risk of changing it.
I think that's
And
exactly the problem of the two capacitors, or this is also
yes,
problem of the analog and digital grounds, which used to be, and it's hard to actually, especially these two multiple capacitors. I think people may be a little bit worried, like it always worked. Now I change it, and it's not going to work, and it's going to be a problem. So why?
hmm right, exactly. So yeah, so I mean, in my case, I remember in one design I did, I was a test engineer at one point. We had used mechanical relays for all of our designs because they have really low, basically almost zero leakage, and very little impedance and so forth. Um, and but the problem is, of course, they're mechanical and they fail after so much time. And you know, it was a maintenance nightmare to kind of keep those boards working. You know, they would buy extra boards, and you know, they desolder all the relays and replace them all, and so on and so forth. And so I decided to just use FET switches on the board, and there was quite a lot of pushback. Oh, is it going to work, and so forth. And it turned out that it worked just fine. But I mean, even if it didn't work fine, you know, I tried to make sure I had time in my schedule to, you know, accommodate a second design spin, and I could
Mm-hmm.
always go back to the mechanical relays if I had to. And so I just, I guess I would urge people to double think whether or not they can have a little risk in their schedule. And if there's a circuit that nobody understands because the guy retired 20 years ago that designed it, maybe think about eliminating that circuit and replacing it. And oftentimes there's options. We do this all the time. We put in multiple options because we're not sure what's going to be the best solution.
I do
And so
same.
we have three options for a circuit that are kind of 0 ohm. Yeah, exactly. And that's a good approach. But oftentimes the idea is like after we're done and we figure out which option's the best, we'll delete the other two options on the layout. But usually that doesn't happen.
I know,
So,
yeah,
you
I
know, I
know
mean,
exactly what you're
if the
talking about.
yeah, if the board has a bunch of blank spaces, maybe you could get a much tighter, more optimal layout if you didn't have that, you know. So anyways, I think that's the
Uh,
top 10 list. Is there
Double
anything we
check,
didn't
because I
talk
think maybe
about?
there are some slides which we didn't show. Three,
Well, we
four.
talked about simulation. We didn't talk about evaluation
Oh
modules.
yeah.
And I guess I would say that evaluation modules we offer for most of our products. And they're a great way of testing out the part before you put it into your design. And some parts are relatively simple and you might test performance, but other parts, you know, like a complicated A to D converter, reading the data sheet can be a little bit difficult. You know, it can be a lot of information. And so sometimes just having the EVM with the software GUI lets you play with the part and try it out, and connect it to your signal sources, and you could learn the device. So the EVM can help you learn the device. It can, you know, allow you to connect it to your real world circuit and adjust the configuration according to what your plan is, and you can make sure that, you know, you didn't miss something and overlook anything. And you could measure performance. And so, oh, and even layout, especially I would say for things like switched power supplies, the layout can be really important. You know, a little bit of part placement that isn't optimal can create extra noise that's unwanted. But even for anything, usually the EVM has, sometimes it has an optimized layout. Sometimes the layout is less optimized because you have to
I
include all
wanted to
these
point out
jumpers and
this,
so
yeah.
forth. Yeah. So it's not always optimal. Sometimes it is. It just depends on the situation. I would say for something like a switched power supply, it's going to be optimal because it won't function properly if you don't do that way. For an A to D converter, probably the things that are close and tight into the converter might be optimized, but then maybe there's going to be some jumpers that'll let you configure it. And so consider the evaluation modules.
I recommend this.
Oh,
I recommend evaluation modules because sometimes what may happen, there may be some features which are not very well explained in datasheets, and you would like to
yes,
understand how it actually works. So you need a real board to actually measure it and test it by yourself.
exactly. Another concept of evaluation models or idea here, we have some little ones that are usually for amplifiers. But let's say that you have an existing design and it uses an old type amplifier and you want to replace it or update it, but you want to just make sure the new device will work, but the package that you're looking for isn't available. Like the original design used an SOIC and the new design uses a SOT or
I
an
didn't know something
SC70
like
or
this
something like that.
exists.
Yeah, it's kind of cool. It's a little board. It just solders right to the pads of the SOIC, and then lets you, So there's the idea here is there's no parasitics, or minimal parasitics compared to if you blue wired it in. If you took some extra long wires and connected it. Before that, we had this dip adapter type EVM, which just basically changes the format of a surface mount device to a dip format. And I still like this. You can, plug this into a solderless breadboard if you like. And it's a good for college students, especially they find that useful. And then similar to the dip adapter is this little coupon board, which is basically op amp configurations in a wide range of different things like inverting, non-inverting, diff amp, filter configurations, and so forth. And the nice thing is all the components are on this, ready for you to solder your device down. And there's footprints for all the associated components that would create that configuration. So we call that the DIY EVM.
Okay.
And I think that's it. Yeah, that's it. So we talked about basically everything on the list. And I think now's the time for the demo. Should
Okay,
we
let's
go to the demo?
Let's do the demo.
Okay. So first, let's look at, let me get the demo software up here. So this one right here has, if you look at the input, there's a common mode signal applied to the input. All the inputs are just soldered together. And we're applying one signal and monitoring that signal with these clip leads. And then the output of the amplifier is right here, and that's going to another channel of the oscilloscope. And here's our power supplies, and there's an instrument over here that is providing the signal, and then 2 oscilloscope channels and the power supply.
So this is basically the first simulation of what we did.
Yes, the common mode simulation. And so I'm going to turn on the signal generator. It's at 500 kilohertz now, and you can see that here. And here's the live signal being captured. And so if you look at the input signal is red, and the output signal is what's feeding through the amplifier. It's on a different scale here. So this instrument allows you to measure. So the peak-to-peak input is 1.6 volts peak to peak, and the peak-to-peak output is 16.6 millivolts. So let's take a closer look at. I'm gonna change the frequency to a higher frequency. I'm gonna make it a 900 kilohertz. And then I'm gonna make this measurement again. And I'm gonna go ahead and make this signal a little bigger on the input. I don't need to. It's fine the way it is. Okay, so if we look at the input signal, it's 500 millivolts, 570 millivolts, and the output signal actually got larger to 14 millivolts peak to peak. And that's because the power supply rejection at higher frequencies is degrading. So I could go to a much lower frequency, for example. And let's take a look at it now. Let me change the scope setting here.
Only 2 millivolts.
Yes, so now we've got about 1 volt peak to peak on the input, but we're getting a very small one, almost beneath the measurement floor of 1.7. So if I were to, well, let's even do it. It's actually a good thing to do. So now it's beyond the measurement capability of my oscilloscope at 40 kilohertz. Maybe I can see a little bit of it feeding through, but you know, the power supply or common mode rejection gets much better at lower frequencies. So should we switch to the other demo?
Yeah. Now we have the second demo. So basically this is going to be the second simulation, what you showed. So it's going to be about the power supply noise rejection, correct?
Yes.
Okay.
So let me show the hardware. So this is the same PC board, the same instrumentation amplifier. And in this case, though, the input's grounded, and we're applying a signal to the positive supply. The positive supply has a DC of 12 volts, and then it has a 1 volt peak-to-peak sine wave riding on it. In order to get that 1 volt peak-to-peak sine wave, I have a power op amp. And the idea behind the power op amp is that driving the power supply, especially with decoupling capacitors on it, it's a little challenging at higher frequencies for a normal signal generator. So you need to buffer that signal generator output. So we're monitoring the power supply, and we're also monitoring the output. So let's take a look at the actual circuit or oscilloscope measurements. We've got 600 kilohertz coming in. You can see the output signal is the yellow signal, and then the input signal is this red signal.
There's the power signal.
That's the power signal, right?
Okay.
And so the power signal is on 5 volts per division right now. And so you can see that it's about 12 volts, about 2 and a little bit, 2 and 10 volts and a little bit of a division. You could kind of see the signal that's riding on top of the supply, but let's switch to AC coupling. So now we're on AC coupling, and I'm going to change the range here so that it's a little bit more obvious.
So this is the noise on the top of the 12 volts.
That's correct. So the input or the power supply AC signal is on a 1 volt per division scale, and then the output is on a 10 millivolts per division scale. And we can see at 600 kilohertz that we're getting about 1.28 volts peak to peak on the power supply, and then on the output we get about 13 millivolts. If we adjust this supply a little bit, now we're getting a little bit smaller input signal. I can boost that back up to make it more consistent. Let's make that about 1.5. And so you can see that the output
Okay.
signal grows a good amount, because we're running at a higher frequency,
Mm-hmm.
and it might not be a sinusoidal output. I could actually pull up on Friday in preparation for this. I took these same two boards and I measured the PSR and CMR, and so you could see it's not exactly what the data sheet says, but it's pretty close. In fact, the PSR looked like it was a little better than the data sheet, but ultimately it's going to be a little different than the data sheet. But that's it. That's the demo, and you could do the same kind of thing with an evaluation board if you want to confirm your power
Can we
supply
go
rejection
lower
or
with the
some other
frequency?
spec.
I'm curious if the noise on the output will disappear.
Oh, yeah, that's a good point. Let me hit stop here. Okay. Oh, I got the frequency set to ridiculous level. So let's change the time base here.
I can already see it. Yeah.
So yeah, you really, unfortunately, the lowest range I have on this is 10 millivolts. Maybe I could
But yeah,
change this to
I
a
can
little
see
bit.
it. There is still noise on the power supply, but it doesn't transfer to the output of the amplifier.
Yes. So there it is at 50. You could kind of start to see it coming out a little bit.
Mm-hmm.
So
So
I guess ultimately,
yeah, go ahead.
I was going to say ultimately the main point is that if you have some common mode noise or power supply noise, the device itself will help minimize that. And you can look at the common mode rejection and power supply rejection spec to understand to what degree that'll happen.
Mm-hmm. So when someone is designing analog circuits, there are more parameters maybe look for than when designing digital circuits.
Yeah, perhaps.
That's the conclusion of this video.
Yes.
Okay, thank you so much, Arthur, for your time and for preparing all these measurements and also all the slides. Uh, I didn't know some of the things. I learned some new things again. I really hope everyone who was watching also learned something new. So that was the goal. Thank you, Arthur, again.
You're welcome. Thanks a lot. Bye, everybody.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEvel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.